A signal arrives at NASA's Deep Space Network. The timestamp reads, 300 hours. Universal time. A computer flags an anomaly. An object crossing the plane of the solar system at a velocity suggesting an origin beyond our sun's gravitational influence. Within 6 hours, 3 observatories confirm the trajectory. Within 12, the object has a designation. Within 24, scientists begin analyzing data that didn't match predictions perfectly. This is how we track visitors from interstellar space. And every detection begins with a question no one can answer immediately. What would you do if you were the first person to see this? The Pan-STARRS telescope in Hawaii scans the same section of sky 4 times each month. It photographs everything, compares images, looks for motion. Most objects follow predictable paths, ellipses, parabolas, curves defined by gravity. But on rare nights, the software detects movement that stands out. An object moving faster than expected, or at an unexpected angle, or both. When astronomers reviewed the data from late 2024, they found exactly this: a point of light traveling through the outer solar system. Initial calculations suggested it originated from interstellar space, not from the Kuiper Belt, not from the Oort cloud, from the region between star systems, the third confirmed visitor in human history, 3I Atlas. The first question was immediate. How fast is it moving? Orbital mechanics obeys strict rules. If you know an object's speed and direction, you can trace its origin. 3I Atlas was clocked at roughly 16 kilometers per second relative to our sun. Fast, but within the range of what gravitational dynamics can explain. What made it noteworthy was the trajectory. It was following a hyperbolic path, meaning it would pass through the solar system once and continue into interstellar space forever. The second question followed instantly. Where did it come from? Teams at NASA's Jet Propulsion Laboratory ran the trajectory backward. They mapped the object's path through space, not just months, years, decades, centuries. If we reverse the motion of 3I Atlas and account for the sun's movement through the galaxy, you arrive at a region of space between star systems. Empty, cold, no parent star, no gravitational anchor, just the interstellar medium. The object had been drifting through the void for millennia before our sun's gravity bent its path slightly inward. This is where observations become more complex. Most comets brighten as they approach the sun. Ice sublimates. Gas erupts. They develop visible tails. 3I Atlas brightened as expected for a comet, but the pattern showed variations. The light curve fluctuated, rose sharply, dimmed, rose again, suggesting the object might be tumbling or venting material asymmetrically, or reflecting light from a surface with uneven features. NASA's infrared telescopes locked onto the signal. They measured thermal emission. Initial data suggested thermal variation consistent with solar heating, though some measurements required further modeling to fully explain. Spectroscopy began. The goal was to identify volatiles, water, ice, carbon dioxide, carbon monoxide, the signatures that define cometary composition. The spectral data showed weak absorption lines, fainter than expected for typical bright comets. This didn't mean the volatiles were absent. It meant they were harder to isolate, possibly obscured by dust, or present in lower concentrations, or released in patterns that made detection challenging from Earth-based instruments. If you're watching this right now, hit the like button so I know you're following along. Even that simple click helps more than you realize. The data created questions that required deeper investigation. If outgassing was subtle, why was brightness changing so dramatically? If the object tumbled chaotically, what caused that spin? And if it came from interstellar space, what else might be crossing our system undetected? Tracking an interstellar object requires coordination across the planet. NASA doesn't work alone. When 3I Atlas was confirmed, observatories in Chile, Spain, South Africa, and Australia began collecting data. Each location captured the object at different angles, different wavelengths, different times of night. The goal was to build a complete profile, shape, spin, composition, velocity. Every measurement mattered. The Hubble Space Telescope was redirected. Hubble doesn't track fast-moving objects easily. It's designed for deep, distant galaxies. But engineers uploaded new pointing instructions. The telescope locked onto 3I Atlas for a 12-hour window, high-resolution imaging, spectroscopy, photometry. The data came back in fragments. No resolved surface, just a point of light. But that point contained information, brightness variations, color shifts, patterns. Ground-based telescopes added velocity measurements. Doppler spectroscopy revealed the object's speed with precision, 16.2 kilometers per second, relative to the sun. But that speed was showing subtle changes. Over weeks, measurements suggested non-gravitational acceleration, small but measurable, and acceleration beyond pure gravitational influence requires explanation. Newton's laws are clear. An object in motion stays in motion unless acted upon by a force. 3I Atlas appeared to be experiencing a force beyond solar and planetary gravity. But what kind? The most likely explanation was outgassing, the release of volatile material creating a subtle rocket effect. This is well documented in comets. Jets of gas can push an object slightly off a purely gravitational trajectory. But here's where modeling became difficult. Visible light observations showed only a faint dust tail, much fainter than bright comets like Hale-Bopp or NEOWISE. Infrared observations detected thermal signatures, but interpreting them required assumptions about surface composition, rotation, and dust distribution. The outgassing rate needed to explain the acceleration was calculable, but confirming it observationally from Earth's distance was challenging. NASA's NEOWISE mission, designed to track near-Earth asteroids, joined the observation campaign. NEOWISE operates in the infrared. It measures thermal emission. The data showed 3I Atlas radiating heat consistent with solar heating at its distance, though some thermal models suggested surface properties might be contributing to the observed temperature. The spin rate added complexity. By measuring how quickly the brightness changed, astronomers calculated rotation. 3I Atlas was tumbling, not smoothly. The light curve showed irregular peaks, a non-uniform rotation. That suggested a non-spherical shape, maybe elongated, maybe irregular, maybe a fragmented structure, or simply an object with uneven albedo across its surface. Spectroscopy provided chemical clues. Telescopes split the reflected light into wavelengths. Each element and molecule absorbs light differently. The spectrum of 3I Atlas showed weak features, neutral colors. No strong emission lines like bright comets typically show. This didn't mean it lacked volatiles. It meant detection was difficult, possibly due to dust obscuring the nucleus, possibly due to lower gas production rates, or possibly due to compositional differences from well-studied comets originating in our solar system. Imagine you were leading this mission. You have only 3 months to gather data before the object moves out of range. What would you prioritize first? Drop it in the comments. By mid-2025, NASA had assembled a comprehensive data set. trajectory, velocity, non-gravitational acceleration estimates, thermal emission, brightness variations, spin characteristics, spectral measurements. Every observation was precise within instrumental limits, and every measurement pointed toward an interstellar comet whose behavior required models to be adjusted to fully understand. Science advances by testing observations against predictions. When something behaves in ways that don't match expectations perfectly, we refine the models, adjust the parameters, add new variables. But 3i Atlas presents a case where multiple models fit parts of the data, but no single model explains everything cleanly. Consider the non-gravitational acceleration. Outgassing is the standard explanation. We've documented it in dozens of comets, but the magnitude of acceleration observed in 3i Atlas requires a certain outgassing rate. When astronomers calculated what that rate should produce in terms of visible coma and tail, the predictions didn't align with observations perfectly. The tail was fainter, the coma less prominent. This doesn't invalidate the outgassing model. It suggests the process might be more subtle: episodic venting, subsurface ice release, dust-rich jets that obscure optical signatures. Radiation pressure is another factor. Sunlight exerts force. For small particles, this pressure matters. But 3i Atlas is estimated to be at least 100 meters across, possibly larger. At that size, radiation pressure becomes a minor contribution unless the object has unusually low density. Some asteroids are rubble piles, loosely bound fragments with significant void space. If 3i Atlas had similar structure, its mass could be lower than size suggests. But low-density objects are vulnerable. Tidal forces, thermal stress, collision history. Surviving millions of years in interstellar space with fragile structure is possible, but requires specific conditions. The shape remains uncertain. Light curve analysis suggests elongation, perhaps several times longer than wide. This is unusual, but not unprecedented. Some asteroids are elongated. Some comet nuclei fragment into irregular shapes. Combined with the rotation characteristics, the elongation suggests 3i Atlas is tumbling through space in a complex pattern. That tumble could be primordial, set in motion during its ejection from its parent system. Or it could result from more recent events, collisions, outgassing jets causing torque, structural shifts. The thermal data requires careful interpretation. Objects in space reach equilibrium between absorbed sunlight and radiated heat. 3i Atlas showed thermal characteristics consistent with its distance from the sun, though some measurements suggested surface properties might differ from typical solar system comets. Dark surfaces absorb more light. Icy surfaces reflect more. The balance determines temperature. If 3i Atlas has a surface layer of dark, carbon-rich material covering subsurface ice, thermal behavior becomes more complex. The spectral signatures remain the most challenging aspect to interpret. Most bright comets show strong emission lines: water vapor, carbon dioxide, carbon monoxide, organic molecules. 3i Atlas showed weak features. This could mean several things: lower volatile content, dust obscuring the nucleus, release rates below detection thresholds from Earth, or compositional differences reflecting its formation in a different stellar system with different chemistry. Does this object change your understanding of how much we still don't know? Write one sentence in the comments. NASA scientists avoid definitive conclusions without sufficient data. They acknowledge that models may need refinement, that interstellar objects might behave differently from solar system comets due to their unique histories. That observation from Earth's distance has inherent limitations. Every hypothesis requires additional data, and Additional data requires time we didn't have. Because 3I Atlas is leaving, the object will exit the solar system within the next 2 years. It will cross the orbit of Neptune, then drift into the Oort cloud, then return to interstellar space. We had one observing window, and we used it to gather every measurement possible. But instruments have limits. Distance imposes constraints, and moving targets don't wait. Imagine standing on a coastline, watching the horizon. Most days you see waves, birds, clouds, familiar patterns. Then one morning, something crosses your field of view. Distant, brief, gone before you can focus properly. You know you saw it, but you can't describe it completely. You can't examine it up close. And you'll never see it again. That's what observing interstellar objects feels like. 3I Atlas traveled for millions of years, maybe tens of millions. It passed through regions of space where no star shines brightly, where temperatures hover just above absolute zero, where cosmic radiation from distant sources is the only interaction. It drifted, tumbled, eroded slowly by micrometeorite impacts. It encountered no planets, no moons, no observers, just emptiness. Then it entered our solar system. A chance encounter, gravitational probability. The sun's influence bent its path slightly inward. For a few months, human telescopes could see it, measure it, photograph it. And then it continued, outward, back into the void. The encounter was brief, insignificant to the object, but deeply meaningful to us. Every interstellar visitor carries information about star formation, about planetary system dynamics, about the materials that exist in the space between stars. 3I Atlas tells us that interstellar space contains debris, fragments, wanderers, objects ejected from their home systems billions of years ago, now adrift. Some will eventually encounter another star. Most won't. They'll travel through the galaxy indefinitely, frozen, dark, unobserved. We are observers, limited by distance, by time, by technology. We build telescopes, launch probes, collect data, but we see only fragments, snapshots, moments in processes that unfold over cosmic timescales. 3I Atlas existed long before humans. It will exist long after. We intersected its path for a brief window, and in that window we learned not everything, but something real. The scale forces perspective. Our solar system is one star among hundreds of billions. Our galaxy is one galaxy among trillions. The objects we detect are infinitesimally small compared to the structures they move through, and yet we detect them. We analyze them. We try to understand them. That effort, however limited, matters because it means we're asking questions. And questions are how knowledge begins. Write one sentence. This makes me think about. The unknowns outnumber the knowns. 3I Atlas is one object, probably one of billions drifting through the galaxy. Most will never be detected. Most will pass through star systems unseen, too faint, too fast, too distant. We catch only the brightest, the closest, the most fortunate alignments, and even those we understand incompletely. But we're improving. Each detection teaches us what to look for. Each measurement refines our models. Each interstellar visitor expands our reference catalog. In 2017, Oumuamua was the first confirmed detection. In 2019, Borisov was the second. In 2024, 3I Atlas was the third. The intervals are shortening. The observations are improving. The questions are becoming more precise. This is not the end. It's the beginning of a longer process. because the universe contains countless interstellar objects, and we're learning how to find them. NASA is building new capabilities. The Vera Rubin Observatory will begin operations soon. It will scan the entire visible sky every few nights, photograph everything, compare images, detect motion. The sensitivity will be unprecedented. Current estimates suggest it will discover thousands of interstellar objects per year. What we consider rare today will become routine observation. Each detection will trigger coordinated follow-up. Ground telescopes, space telescopes, spectroscopy, photometry, orbital tracking. The data will accumulate. Patterns will emerge. We'll categorize interstellar objects by composition, by size, by trajectory. We'll build a statistical census, and from that census, we'll infer the population. How many objects drift through the galaxy, where they originate, how they formed. The James Webb Space Telescope can observe fainter objects than Hubble. It operates primarily in the infrared. It can detect thermal signatures and molecular features that visible light telescopes miss. When another interstellar visitor arrives within observing range, Webb will study it, measure its temperature more precisely, analyze its spectrum with greater detail, search for specific molecules. The data will be higher resolution, more sensitive, more revealing. Spacecraft missions are being proposed, not to 3I Atlas, it's too far now, but to future visitors. Imagine a probe waiting in orbit at a strategic location, ready to launch when an interstellar object is detected early enough. It would intercept, match velocity, fly alongside for days or weeks, take close-up images, measure surface properties directly, sample any outgassing plumes, transmit detailed data back to Earth. We have the technology. What we need is early detection and rapid response capability. The Comet Interceptor mission, planned by the European Space Agency, uses this strategy. It will wait at a gravitationally stable point in space. When a pristine comet or interstellar visitor enters the inner solar system, the probe will activate, adjust its trajectory, intercept. The same concept could revolutionize how we study these objects, but it requires readiness and favorable timing. 3I Atlas is still visible in large telescopes. Barely. A faint point of light in the outer solar system. It's dimming as distance increases. Within months, it will fade below the detection threshold of most observatories. Within a year, routine observations will end, but the data remains, archived, available for reanalysis. Future scientists will apply new models, test refined hypotheses, compare 3I Atlas to subsequent detections. The object itself is leaving, but the questions it raises will drive research for years. And somewhere in the galaxy, other objects are traveling, drifting through the darkness. Some are heading in our general direction, not intentionally, just probabilistically. In 10 years, or 50, or 100, another visitor will arrive close enough to study, will detect it earlier, track it longer, study it more thoroughly, and it will raise new questions. Because each visitor is different. Each carries its own history, forged in a different stellar system under different conditions. We don't know what we'll find next. That's the entire point. The unknown isn't a barrier. It's why we build telescopes, why we train scientists, why we fund missions. Every observation, every spectrum, every data point, they're pieces of a puzzle we're only beginning to assemble. 3I Atlas is one piece, a small piece in a vast picture, but it matters. The galaxy is older than human civilizations can truly comprehend. Stars have formed, lived, died, exploded, scattered their material. That material condensed, formed new stars, new planets, new debris. Some of that debris was ejected into interstellar space. It's been traveling ever since, and occasionally it passes through our neighborhood. We're fortunate, not because we're special, but because we're here, alive, observing, asking. The universe doesn't require our understanding, but we require it, and that makes all the difference. The unknown isn't empty, it's teaching us to look further